Greetings, everyone. I'm Professor Lawrence Pace at the National Intelligence University, and I am about to walk you through the QMI initiative that I am working with a diverse group of colleagues in the quantum computing arena. And now what I would like to walk everyone through is just to see what we've done up to this point and some of the people who have been instrumental in the background. What you see here are a distinguished panel of faculty who have come together, and I'm highlighting Dr. Mark Hodgman, who is speaking on quantum. He is one of my colleagues there at the National Intelligence University and serves as an advisor to the team. So one of our distinguished members, QMI members, is Dr. Joanna Szynski and the Quantum Lab here. Now, this particular page gives a snapshot of our actual facility. It's in our courtyard there at NIU, and you're seeing a picture of the faculty and students and what the setting is like when we all come together to do academics and do our various research on campus. Now, what I want to get into now is to talk about what we're doing. What we're doing now is producing a book on quantum future and roadmap to achieving quantum secure, ready advantage. And this will be in the support to the quantum community and those who will be able to benefit from quantum as a whole. The faculty and students will help in achieving this objectives by one, students working and being involved in the knowledge graph of quantum sensor pipeline, including portal provided knowledge of institutions, subject matter experts, specs, metrics, IP rights. Also, they will be under the guidance of myself and other faculty members, Dr. Meir Gassai, Dr. Melissa Leduc, in an academic environment where we will lead the cohort researchers in an environment to focus on assessing technical readiness of the respective sensors in the pipeline. There will be editing, reviewing specs, metrics, assessing, and selecting from drop-down lists of technical readiness levels. Now, the question from many of you that are listening into this update is the question of benefits to the community. The benefits to the community, it will help facilitate transfer from lab and the field, deployed in real-world applications as technology matures. So we're looking at industry, academia, and government. This is something that will support QMI's quantum ontology development. Also, a couple of other benefits will be tech transfer from the lab to the field users as technology matures. And lastly, the adoption of quantum through tech transfer, which can be a huge boost to the US economy. Welcome to the QMI Initiative virtual session. Speakers that you will be hearing from today are speaking on their behalf and not their affiliation. I'd like to introduce Dr. Terry Jansen, who works quantum at the Defense Intelligence Agency. We also have Dr. Barry Smith, who is with the University of Buffalo and a professor of philosophy. We have Dr. Meir Gassai, NGA chair at the National Intelligence University, working in the School of Intelligence and Technology. And yours truly, Lawrence Pace. I am professor at the National Intelligence University and also working in the School of Technology Intelligence. Let's get started here. The first question for Dr. Smith: what is quantum metascience?
This is almost easy to answer. So we have quantum science, we have quantum engineering, we have quantum communications, quantum sensors, quantum experiments. So there are many things which are going on in the quantum domain. The general background to our present meeting is the desire to pay attention to the issue of quantum dominance. That is to say, we want the US to keep pace with any adversary in developing those areas of quantum engineering which are relevant to, for instance, defense and security. And so quantum metascience is an attempt to find a way of having an overview over all that's being achieved from one day to the next, all the data, all the devices, all the experiments, all the algorithms, all the training, all the patents, all the new enterprises. We have to keep pace with all of those things. We have to work out what people are doing, and we have to find ways of maximizing the benefits of what people are doing. And we have to find a way of measuring those benefits in relation to what other people, for instance, in China, are doing. And then the question is, how can we do this? Given that quantum science and engineering itself is so complicated, how can we do quantum metascience? And that's the next question, I guess.
That's exactly right. That's a great segue to what I was going to ask you next. Not to offend anyone, but isn't metascience only for ivory tower intellectuals?
So scientists like to go on doing what they do, and they're good at doing what they do. And we shouldn't try and interrupt them or tell them that we can do it better because we have some kind of meta level where we live. The problem is that sciences are scattered into different threads and strands and silos, so that not all the scientists talk to all the other scientists. Not all the codes and labels and terminological expressions that scientists use are common to all other scientists. And also, some scientists speak Chinese, and so they describe what they're doing in a way which is skewed to the way what we're doing is described. So what we need is a way of having an overview. It doesn't have to be a perfectly detailed and precise overview, but it has to be an overview which will enable us to compare what's happening in different areas of quantum science and of quantum engineering. And that's what quantum metascience is supposed to be. And it would indeed be an impossible project if we were dealing with all of science, because physics and biology are huge. And there are huge numbers of journals, huge numbers of data repositories, huge numbers of people involved. Quantum, however, is still a relatively small effort. And we're still at the beginning along many threads in working out whether we can do quantum engineering of specific sorts at all, because the challenges are so great. So I think the idea of quantum metascience is actually quite reasonable. In 10 years, it probably will not be a reasonable idea, but now we can get hold of it. We can get hold of this beast, and we can build something which can be useful in making the beast develop in the most effective ways. That's the assumption, anyway.
Well, Barry, that's a really good segue to my next question for you. Ontology is really taking on a life of its own. So if you could describe what is ontology, but more so, what is the role and how does that play into quantum metascience?
Good. So you described me as a professor of philosophy. In fact, I have affiliate professor positions in the Department of Biomedical Informatics and Computer Science and Neurology. And that's because my original ontological work, my applied ontology work, was not with philosophers, it was with scientists working particularly in biology and medicine. And there I was involved in the very early attempts by biologists and clinical scientists to make use of the results of the new Human Genome Project. So we had suddenly a huge amount of new data, new technology, new devices, new methods, new repositories, which were supposed to be relevant to understanding health and disease. But the clinicians had no idea what they could do with this data because it consists of long strings of letters of the alphabet. And so I was not at the very beginning, but near the beginning of the effort to try and solve this problem by devising a controlled vocabulary which we called an ontology, the terms of which were used to label strings of DNA or strings of other kinds of ribonucleic acid, proteins, RNA, and so forth. We labeled them using words which biologists and clinicians can understand, words like cell division or perception of blue light, things which are important to biologists and which are associated with specific gene sequences. That was tremendously useful. And so the idea of building what was called the gene ontology was generalized. And now we have anatomy ontology, we have chemistry ontology, we have protein ontology, we have disease ontology. Wow. And all of these ontologies are used to provide controlled vocabularies so that biologists and clinicians will use the same terms when talking about the same data. And now what we're trying to do with quantum metascience is apply exactly the same ideas, namely tagging new kinds of data, new kinds of experiments, new kinds of algorithms, using a controlled vocabulary called an ontology. And actually we'll have several ontologies. We'll have an ontology for physics in general. We'll have an ontology for the different branches of quantum physics. We'll have an ontology for quantum engineering. And then we'll have another ontology for what we don't have a good word for yet, but basically it's quantum military industrial developments. So who owns the patents to which quantum invention? Where are the really dangerous experiments being carried out? Where is funding particularly available for these kinds of sensors? That kind of information will belong to another area where we will need terms like invention, patent, and so forth. And I think that's probably enough. That the whole thing is quantum metascience.
Well, that's really good. And I appreciate, Barry, how you set the stage. And this is where I appreciate you, the panelists, the speakers here, to just flow with me. This was a trigger. This is the trigger question. And I'm going to come to Terry and even Mayor, if you choose to chime in, but many don't understand what quantum scientists and engineers are talking about in the areas of quantum communication. Can you shed a little light from that perspective?
Well, sure, yes. And as said, I'm speaking on my own behalf and not my employer. And one of the problems we have with stakeholders, with people that are funding quantum, with people that can use it, this is across the board in industry, government, academia, across the globe in every country, is that those that are not quantum physicists and those that don't understand quantum mechanics or electrodynamics have a hard time really understanding how they can use quantum. And the nice thing about the quantum ontology is that it puts everything into a common language, and it represents things just as we do in our heads and our brains from birth. It compiles a model of all of quantum, which gives us many, many advantages. Not to say that we have the human advantage and also the machine readable advantage, because now our artificial intelligence can read the ontology just as we can read the ontology. And so, for example, if you're developing a system, so you're doing a commercial satellite to ground communications station, and you want to use quantum communications by entangling photons between space and ground, just as is done in China across a stretch of 3,000 miles. That's something which is not all that easy for an ordinary engineer using classical equipment to understand. And the quantum ontology solves that problem, because now everything is related in terms not only in the language of the quantum physicists and others that are professionals in the engineering of quantum side, but also in the language of the domain of the user, of the developer, so that we can cross between the different perspectives and languages of the different user groups.
This is the video that we're doing. Yeah, are you fine?
That's probably enough for now.
Thank you, Terry. So one of the things that, as building off of the discussion that we've had and what Barry just touched on, and now it brings to mind myself as a professor at the National Intelligence University. You put me in the mindset of how do I, and Mayor can speak on this as well, envision students being involved with QMI? One of the things that comes to mind is coordinating and setting up a cohort. And cohorts at our university, it can range anywhere from 1 to 5 students, but even if we show or there's an expression of more than 5, we can still accommodate that. But I look at that as being an opportunity where our students, because of the environment where they can do different types of research, all the way from unclassed to classified, whatever that may be, we would be able to work with the students and help facilitate transfer from lab and the field to real world application and the technologies to help mature different things within QMI. Mayor, do you have any other thoughts of what that may look like? That's just my view as a professor working in the classroom with the students.
Yeah, I think there's a lot of opportunities for the students to learn, based on this initiative. And then a lot of things that Barry had talked about in terms of developing an ontology would essentially provide a baseline knowledge for the students, particularly those that are coming in may not have background that would qualify for them to do some empirical work in quantum. But should that base knowledge exist, then they can contribute to the knowledge for the QMI initiative, for sure.
Excellent. And Mayor, if you don't mind, go ahead and build off of what you just touched on, because I know you've already have been working in this area. If you could talk about what are some of the tools that we would provide the students in order to do some of those things, i.e. the QMI portal?
Yeah, no, that's a great question. So I think in the years to come, artificial intelligence is expected to assist in all major developments and completely change the way things are going to be done today, right? So it's unlikely that it's going to be inseparable from a helping hand in all major industries, and we're starting to see a lot of that. Currently, there are several tools at NIU that we use that students are exposed to. The one that comes to mind is scikit-learn, which is a machine learning library for Python that our students use. And they use it for image classification, for example, pre-processing, clustering algorithms. And to take that knowledge and having access to quantum science organization's portal, our students can learn and do further research. For example, they could access and utilize Amazon's Bracket, for example, and then a complete library of quantum algorithms that are being developed in the QMI initiative. And then in turn, they can contribute to the knowledge base in quantum computing.
That's great. And what you just made me think of that I would like to share with the community is that this initiative that we're discussing here can be a huge boost to the US economy. So when I think about the faculty, the things that you and I, Mayor, are doing at the National Intelligence University and working with our students, getting them involved will provide value to all of those things, to include just the huge impact in some things across DoD as a whole.
Right.
So I have another thought with some things that as we're building on these questions and telling our story, Terry, I'm going to come to you because I was thinking about what kind of knowledge for quantum sensors do we need to go in the knowledge graph for technology transfer pipeline to make it useful to potential users of that technology?
Yes, a very good question. Again, speaking on my own behalf, the quantum sensors are a technology which is evolving from a fundamental basic research into levels closer to being able to put them in test environments and eventually get them into real life production. And this pipeline is really quite complex because the sensor types differ immensely. The atomic species used in those sensors differ. The applications differ. The reliability differs. The temperature operating ranges differ. And so we have a vast amount of knowledge just about how to even describe these sensors. But now consider even making a decision on which sensor to choose in the pipeline. Because you might have sensors from technology readiness level 1 all the way up to technology readiness level 9, which is ready for production in the deployment. But in order to make a good decision, you need to understand how those sensors perform. And so in this ontology-based knowledge representation, all sensors have all their specs and metrics included with the knowledge in the repository. That makes it very easy for us to push a button to do an ad hoc query and say, look, I want to see all sensors which might be applicable for use in this submarine, which is going to be deployed in 5 years, or even a commercial application like a satellite. And so you would almost instantly see from our knowledge repository all of the sensors which meet the requirements, specs, and then you would see all the performance metrics. And that can be contrasted now to the classical sensors. And you would see, as part of this automatic generation, the percentage differences between performance. And in some cases, with some sensors, you see 500 times the performance of a classical sensor. The shortcoming today is that very few people in the classical world, and engineers that are building things with classical technology, have the slightest clue to what's in this pipeline. And this pipeline is remarkable. It's immense, but it's complicated. It's hard to understand. It's hard to get your head around. If you can have this quantum ontology-based knowledge repository on quantum sensors, that means all knowledge is there and can, at a push button, be retrieved for many different uses. Let's say, for example, you're a commercial provider of a satellite and you want to compare the various classical to quantum options for your satellite. You would do this ad hoc query, or maybe you do a request for information to the system. Now, you specify this request for information or even a request for proposal in these ontological terms. It is the language of the ontology. So now when we submit that request to the quantum science organization's knowledge repository, it instantly goes and does a precise match, not a close enough match, a precise match to the exact requirements of the sensor hardware, and it captures the metrics, performance metrics, and now we can automatically spin up comparisons, and we can actually automatically generate even like Excel spreadsheets, which put in column A these quantum defined specs, these quantum defined metrics, even the quantum defined intellectual property acquisition rights to see how you could buy it or how you could maybe get it from some third party. And so now, if you combine that with the classical sensors and spin them up together, you have now instantly made available to the classical designer of that satellite or that submarine or whatever you're building the options in the pipeline with technology readiness levels. And so now the commercial satellite provider might say, well, look, I won't deploy my satellite until maybe 2025. Well, we might have enough time in there to invest some money and take that from technology readiness level 3 or 4 up to maybe 5, 6, 7, or maybe even get to 9. And if we do that, as we mentioned, the performance gains are immense. And if we're going to compete in this global race, this quantum race to quantum advantage, quantum everything, then we need to be able to do things quickly. This is the solution to that problem.
Wow. Terry, I really appreciate what you just said on the end, because that was going to be one other part of the onion I was going to peel, as to ask you, we're in a great quantum race, and what does that look like? And you really tied a bow on that one to bring that in, which leads me to another point is how can NIU and NIH students contribute to quantum metascience? Now, we have to be mindful that if these students don't have the background, or if they do have the quantum knowledge, then ontology, quantum technology evaluation, population technology transfer pipeline. So thinking of the fact that we may be looking at a very diverse background, but how we can be inclusive to bring all of that talent to the table. So Mayor, just want to come to you with what do you, this is probably one of those other envisions, you know, how do we see that? And because of academia, just to give you some time to think about what I just asked there, Mayor, one of the things that I know that we can build on when you think about the community that we're in from academia is when you think about how this will service and benefit quantum, looking at industry partners, looking at manufacturers, providers of quantum, first and foremost. And then also, as I touched on earlier about the huge benefits, this is going to be a huge benefit to us, the United States, the government, DoD, IC, NATO, Five Eye, and academia as a whole. So any thoughts, any opinions there, Mayor, from when you think about the students in that population?
Sure, that's a great point, and I think there are lots of opportunities, to contribute to the knowledge base. So if, for example, if the notion of technology transfer includes some collaborative process, then it's important that the solutions that we come up with for the global challenges, it would play a crucial role in moving the inventions from inventors for creators to the wider public, right? And this is where the university can help out tremendously. So having access to tools, data, knowledge from the Quantum Metascience Initiative will enable our students to take advantage and take the knowledge that they gain and apply to real world problems and challenges. And another way that the students can contribute to the QMI initiative is to be a test bed and contributors to the data ingest and the quantum bibliographic and the development tools and the databases that Barry had talked about earlier. And so in turn, it can kind of feed the cycle of not only providing the students a place to go to for authoritative resources, but also contribute from that perspective as well.
Great
point. Maybe I can say a little bit here. So my idea would be something like this. The teacher in the classroom is talking to the students about quantum sensors. And so they learn general physical principles governing quantum sensors. But then they're part of a cohort which has a project to create the ontology of quantum sensor manufacturing or something like that. And so they take what they learn in the classroom and they take the ontology. There will be a part of the ontology, a kernel of the ontology already there for them, but they will find a need to add new terms because they will find that there are 4 companies building that particular type of quantum sensor in America at the moment. And then they will have the challenge. What information can they get from those companies? How will they then use the ontology to describe that information so that they can do comparisons of the sort which Terry was talking about earlier? And that means that their theoretical learning is being made a real world relevant.
Yes.
Not by having them build their own quantum sensors, but by having them gain an overview of an important part of the quantum sensor industry. And that kind of opportunity will repeat itself over and over again. And every time they build such an overview, they are contributing to an artifact which is growing all the time, which is of tremendous significance and will become more significant as time goes by. Something like that happened in biology. I was a part of it. And there were students involved building the ontologies as well as faculty members. And the ontologies made a big difference to what became a world revolution in ways of doing biomedicine. In China also, incidentally. So the ontologies that were built to support the transformation of biology and medicine have had billions of dollars invested in them over time. More is being invested all the time because they're so useful.
Wow. Well, Barry, thank you for that. We're going to bring it in, but before I bring Terry, please get ready. I have a closing question for you that I really feel that will bring everything home. But let me just add just one piece to what Barry just said. This truly does, when we talk about benefiting to the community, this truly is conventional in the sense that it will help facilitate transfer from lab to the field, but even more importantly, how it's deployed in real world applications as the technology matures. That's key. So with that said, Terry, would welcome to hear your thoughts, your perspective on what does the initiative that we're working, this plan, what do we plan to accomplish this year as a collective team, as we collaborate on this important topic?
Well, yeah, good question. So speaking on my own behalf again, we have grand plans for 2023. We have the portal up and running in beta form. People are using it in limited capacity. It'll be up in full beta form here within the next coming weeks or months, hopefully within weeks. And we'll be able to start in this beta form, engaging people. They can drag and drop their specs and metrics for quantum sensors or quantum computers or quantum communications devices for satellites and ground communications and the like. And we can start almost from day one being of value. And so some initiatives are basically years out. You put a lot of money up front and you get little for return until decades later, maybe, and maybe you never get return on investment. But in our case, we're in this arrangement with collaboration with universities, collaboration with academia, also commercial and government collaborations. We have a core already. We have a resource capability. We are already starting to see some of the fruits of our labors. We meet with organizations like, we've had numerous people involved in the Quantum Economic Development Consortium. And we've had, a number of other engagements with commercial providers, from startups all the way to Fortune 500 like IBM, Rigetti, IonQ, the big manufacturers of the big quantum computers. And so with this kind of collaboration and with especially cohorts like you're talking about, where we have students getting involved, we're doing many things of great value on day one. Let's list those out. Number one, the students are getting knowledge of quantum. Number two, the students are doing things with quantum that has real use to quantum stakeholders, such as manufacturers, such as designers, people with requirements for sensing. And one thing that people don't understand, this is the third big advantage, is we are getting in front of people that don't know quantum, the fact that they've got a quantum alternative. And not only do they have an alternative, but in some cases that can be a 500 times performance improvement. And to not know that when you're in a quantum race is really unthinkable. You've got this global race going on and people are clueless as to what quantum is. And we can get that in front of them and make it intelligible and make it easy and make it fast. And the students, the faculty, the volunteers for the initiative, all of this can come together with really, in terms of investment, a minimal investment with huge gains. And so now we're talking about return on investment, which is in very, very short order. Probably this year, we're going to get more, we will have more return than the collective time of the people that put in the time on this thing. This is a volunteer effort. This is strictly a nonprofit endeavor. But, the point is that one of the nation's priorities, and this is something that the president has put out. If you take the quantum sensors report that he did last year, we can provide that reference. Speaking of references, we have 3,000 quantum references that we can provide on demand through the portal to anyone that needs them when the portal goes live. And we won't go live until we have done the major publication that we're planning to do this year, which will tie it all together with the capabilities of the infrastructure, the people, and the knowledge that we're trying to get in front of people that need to know it. And so this is so important that the President of the United States has done a number of things. One thing he's done, he's encouraged the Defense Department to put out the National Security Memorandum number 10. This follows number 8. These are executive orders to advance quantum in a number of areas. First, to protect against quantum, because if we were to run Shor's algorithm, I'll give a little history here. Shor's algorithm is referring to a professor at MIT that back a few years ago wrote a program for a quantum computer with quantum mechanics that was able to factor prime numbers. Now, the significance here that is if that program were to work on a quantum computer today, your bank accounts would be drained. Your secrets would be known. All of the government secrets would be known. It would be worse than World War II's atomic bomb. This is called, we've heard of references to the current Manhattan Project that some of the others in the race are doing today. We can't lose this race. We must win this race. The stakes are catastrophic. It is a total game changer, not a partial game changer. It's game over for the United States and for anyone in the free world that wants to maintain democracy.
Wow.
So the initiative starting from this year is doing things that helps us fix the problems we've got in the quantum race. With that, let me defer back to you. Anything more I should say about that?
I think you've covered enough for this first conversation, because I want to leave the audience and listeners itching and waiting for us to come back with an update.